Welcome back to my channel. Today we'll be learning about circular motion. We have just seen in my last two videos, we have seen laws of motion and friction. So today we'll be seeing circular motion. The topics which I am going to cover, you just see the in circular motion, that is angular position, angular velocity, angular acceleration. So these are the topics we are going to cover. Then we'll just going to cover equations of motion in circular motion. We are also going to see the relation between linear and angular velocity in circular motion. Okay, then we'll see that tangential and centripetal component of acceleration. We'll just see little bit about the dynamics of circular motion. Then we'll see a very important topic, that is circular turning and banking of roads. Okay, and last we'll just see a little bit about the centrifugal force. Okay, first is centripetal force, then centrifugal force. Okay. Let me start with circular motion. It's a very important topic. Okay, please pay attention. Okay, circular motion. Let me draw a circle first and we'll start with the basic things. Okay, let's say, okay. Now, here, let me draw two axes first. Two axes of this circle. This is a vertical axis. This is my horizontal axis. Let's say a body is rotating in the circular path on the circumference of the circle. So I'll just say that the present location of the body is P. Okay. So if I just connect, let's say this is my center. From this center, I'll just connect. Okay. So naturally, this will be the radius. And what is the, at what angle? Let's say the angle is theta. So the present position of the body is at P, which is at an angle of theta from the horizontal axis. Okay. Now the body is traversing a path in the circular orbit and it has reached a new position which I am marking it as P dash. Okay. What is the angle traveled? That let it be delta theta. Okay. That is the incremental angle that it has traveled. Okay. So now what will be theta? What will be theta? We can write it that theta, which is the present position of the body, that will be called as the angular position. The angular position of the body. New terms will be learning, angular position. Okay. Now there is another term that is called omega, that is the angular velocity. We have seen linear velocity, linear speed. Now this is angular velocity. So how do I define that? Rate of change of angular position. Rate of change of angular position is called angular velocity. Okay. How do I define it? Rate of change of angular position. If you see the diagram, initially the position was P at an angle theta. Now it has changed to P dash. It has traveled theta plus delta theta. Okay. So what is the rate of change of angular position? It will be defined as omega is equal to limit delta t tending towards 0. That is incrementally small time, infinitesimally small time. Okay, delta t is tending towards 0. So delta t is tending towards 0. Delta theta, that is the incremental position change, divided by delta t, that is actually omega. Okay, so this is a very definition of a differentiation. We can also write it as d theta by dt. So omega can be written as d theta by dt. Now angular acceleration, alpha is your angular acceleration. So that can be written as alpha equal to d omega by dt. So d by dt of d theta by dt. So we can write it d2 theta by dt square. Okay, this can be written. We'll just write the basic laws of motion applicable to the circular path. Okay, so that is your omega equal to omega 0 plus alpha t, theta equal to omega 0 t plus half alpha t square, and omega square equal to omega 0 square plus 2 alpha theta. Okay, if I draw an analogy, so this thing can be compared to v equal to u plus at in linear motion. So you can just compare between circular and linear. So we are just trying to draw an analogy. Okay, so this is theta is the position, s is the distance for linear. So s equal to ut plus half at square, and this was omega. Omega is the angular velocity, final angular velocity. Omega 0 is the initial angular velocity. So here also v square equal to u square plus 2as. So this is the way we can write down a similarity between the circular and linear equations of motion. Okay. Now I'll just find out the tangential and centripetal component of acceleration. The linear distance p dash. Let me go back to the figure. Here you are seeing that the when the body has traveled from p to p dash, it has traveled an arc. What was the arc length? p dash arc. Now, if I consider this straight line, if I join this, if I join this with a straight line like this, now what will be the straight line path? That is the shortest distance. How do I write that? Linear distance that is p dash traveled by the particle in time delta t is delta s. What will be delta s? Let me just mark it. This is delta s. This is delta s. Okay, this one. Did you notice? This one. This is delta s. Okay. So here, this one is delta s. So what we can write? Delta s equal to r delta theta. As delta theta is very small, that is why we can write it. Okay. Now delta s by delta t equal to r delta theta by delta t. So we can write delta s by delta t is v, that is the linear speed, is equal to r omega. So this will be my linear speed and this is my angular velocity. So we can write v equal to r omega. This is a very important finding. V equal to r omega. V is the linear speed. We are just correlating linear with the angular. Okay, linear speed. V is equal to r omega. Okay, that we can write. Now we'll see that the tangential component of acceleration is dv by dt. How do I mark the tangential component of acceleration in this figure? I'll just rub these things a little bit. And this was p. So as it was going, the tangential component of acceleration, if I draw a tangent here, so this is my direction of tangential component of acceleration, which I am writing as dv by dt. There will be a component towards the center, that is the radial component. We also call it that direction to be this direction to be centripetal component of acceleration. So tangential component is this one. Okay, centripetal component is always towards the center, which I am marking at AR. I'm just coming back to it, the derivation part of it. Okay, so AT is the tangential component of acceleration. This can be written as d by dt of r omega. I'm just writing this from there. Okay. So that is equal to R is constant. So R d omega by dt. So it can be written as R alpha. R alpha. Okay. So this is my tangential component of acceleration. Tangential component of acceleration. Okay. Now the acceleration in circular motion. There are actually two parts. Acceleration in circular motion. One is tangential, one is centripetal. Acceleration in circular motion. Okay. Acceleration is a vector quantity, so I am writing it in the form of vector minus omega square r e r. I'll just tell you what are the meaning, plus dB by dt into et. Okay, where er is the unit vector along the radius, so it is the radial component, and et is the unit vector in the tangential direction. Okay, so here minus omega square r, minus we are writing because the radius vector is away from the center and the centripetal component is towards the center, that is in the other side, the opposite side. That is why I'm writing minus omega square r. Okay. So, and ER and ET, as I told, that unit vector in the direction of radius is ER, and unit vector in the direction of like the tangential direction, that is ET. Okay. Now, if the circular motion is uniform circular motion, if it is uniform, so velocity is not changing. So that means dv by dt is 0. So in that case, acceleration becomes minus omega square r er. It can be written like that. Now this, the mod of that, that is the magnitude part, will be omega square r. Okay, and ar, this is nothing but ar will be omega square r. So omega square v equal to r omega, that we have seen just now. So this can be written as v square by r square into r. So v square by r. So the tangential, the radial component of acceleration can also be written as v square by r. Okay. Now this was the case for the uniform circular motion. The velocity is not changing. That is why the tangential component at, this is nothing but at, is 0. Okay. Now if it is non-uniform circular motion, if it is non-uniform, in that case ar is minus omega square r and at will be dv by dt. And if you draw this thing, like if you draw a circle, then we have this, I am marking it as the center. So you have a component towards, that is your v square by r. You have a component out here, that is along the tangent, that will be dv by dt, and you have the, that is a, that is the resultant one. Okay, so a can be written as A can be written as square root of AT square plus AR square. Okay. So that is square root of dV by dt whole square plus, so that will be positive only. So V square, because I am squaring, that is why. Okay, and alpha will be this angle. So this is alpha. That is, alpha is the angle of the resultant acceleration with the radial component or the tangential component. Okay, so tan alpha is written as dv by dt divided by v square by r. Okay, it can be written like this. Okay, so we are seeing the acceleration components of the circular motion. Let me see little bit about the dynamics part of it. Dynamics means force will come. Dynamics of circular motion. So force will come in the dynamics part. So if the speed remains constant, if the speed of particle remains constant, then at equal to 0, that is dv by dt is equal to 0. Okay. So only what will be there? So only AR, that is it is there, only AR is there. Okay. Now AR is V square by R. So what will be the force? That is the force towards the center, that is mass into acceleration. So that is equal to mass into V square by R. So that we call it as centripetal force. Centripetal force. Okay. This one is very important. How do you define the centripetal force? That is the force acting towards the center. Okay. We'll see a very important topic next. That will be like the topic under consideration. That will be circular turning and banking of roads. Circular, it is very important. Circular turning and banking of roads. The physics of which is very interesting. Why we do banking of the roads, how it is a very important consideration for vehicles moving at a very high speed and taking a turn. All these things we are going to learn. Okay. Again, let me just draw a circle. Okay. Let me draw another path, that is how it is going inside. And there's a vehicle which is going in this path, like the vehicle is going in the circular orbit. It is not going straight, it is going in the circular orbit. Okay. So we have to understand one thing very carefully, that moment a body wants to traverse in a circular path, the body will have a tendency to slip in the tangential direction. Okay, so you have to continuously steer the vehicle. Otherwise, it will, out of inertia, it will steer away from the path which is in the tangential direction. So, in order for the body to be kept in the orbit or in a circular path, a constant force towards the center is going to act. That constant force towards the center will only keep the body in the circular path. Otherwise, if the force is not existing, the body will slip tangentially and it will go out. Okay. So that physics we already know it. Okay. So if it is only going this way, then naturally this is the road. Okay. This is the road. So what is going to act towards the center? only friction is going to act towards the center. So the frictional force will be towards the center. The frictional force will actually prevent the body from sliding away or going out of the track. So the frictional force is towards the center, that will be very much instrumental in keeping the body in the circular path. Okay, so if I just draw the free body diagram of the body, if I just draw the free body diagram of the body, it will be like this. Let's say this is the body that we have considered. This one, what I mean to say. Okay, this is the body that we have considered. So here the normal reaction is up from the road. We have mg, that is down, and we have a friction force, static friction force, that is acting towards the center. Okay, now this fs is equal to mv square by r. So right now we understand that this is mv square by r. Now fs is the limiting friction, because if it is crossing that limiting value, friction will no longer be able to hold the body in the steady state condition, So if it is limiting value, so fs is the limiting friction. Fs is the limiting friction. So Fs is less than equal to mu s into n. Now we can write it that from here that mv square by r is less than equal to mu s into n. So here I can write that mu s is greater than equal to mv square by r into n is greater than equal to mv square by r into mg is greater than equal to, m gets cancelled, so v square by rg. So this will be mu s. Okay, so this will be mu s. So that is a very important part for circular motion. So here we can write that friction is self-adjusting. Friction is self-adjusting to prevent a vehicle from skidding off the track. But friction alone is not always sufficient. The body is trying to take a circular, like moving in a circular path, and it is trying to take a turn with a velocity v. Okay, the body is not skidding. I told that if the body has to remain in a circular path, it has to always have a acceleration towards the center. If that acceleration component is not there, if that force is not there, which is towards the center, the body will tend to slip in the tangential path because of inertia. Now there should be a centripetal component of force that will prevent the body from skidding off the track. Okay, when it is accelerating in a circular path. So here we are seeing that mu s is greater than equal to v square by rg, but mu s is always not instrumental in preventing the body from skidding or sliding or toppling, Okay, so we need to suffice, like we need some other force which is also acting in the towards the center in addition to the friction force, so that the body can negotiate a turn at a much higher speed. In that case, we require banking of roads. Okay, it's a very interesting thing, banking. So we will just note one thing, that the body will need a force in addition to the friction force. Okay. So what I was telling, that mu s we found it, and we want to negotiate a track at a much higher speed. So in that case, I just need banking of the road. So I'm just drawing two inclined faces. Okay, So there is a two inclined faces. So this you understand, this is just the road itself is inclined like this. The road itself is inclined. We call it, it has banked. Okay. And if I draw the this is the center line, okay, and let's say the body is out here. I'll just make it little bit bigger. Let's say the body is out here. It is negotiating a turn on a path which is not horizontal, which is inclined. Okay, so if it is inclined, naturally there will be a normal reaction force that will be at an angle. Okay, now that normal reaction force from the road to the body is acting at an angle. So if I just draw there will be a vertical component. Let's say this is n cos theta, and there will be a horizontal component towards the center that will be n sin theta. Of course, mg will be down, and this will be the radius of the path. Okay. So now you see, when the body is sliding at an inclined plane, there will be a normal reaction force which is perpendicular to this surface. Let's say this is 90 degree, of course. So this normal reaction force will have a component n sin theta, and n sin theta will be towards the center. So n sin theta will act when the body is negotiating a banked road. N sin theta will be there in addition to friction force. Okay, which will help the body to take a turn at a much higher velocity than it would have been negotiating had the surface been plain. Now the surface is banked. Had the surface been plain, the body would not have negotiated a turn with this much higher speed. What it can now do if the surfaces are banked. So in addition to friction, there is a component of force n sin theta towards the center that is actually helping the body to take a turn at a much higher speed. So what I can write, if I just am writing this thing as n sin theta is equal to mv square by r, because this is the centripetal component of force. Okay, n cos theta is equal to mg. I'm just balancing the mg with n cos theta in the vertical direction. So this is equation 1, this is equation 2. Okay, now if you just divide equation 1 from equation 2, so n sin theta by n cos theta is equal to it will come to be v square by rg, and here it will be tan theta is equal to v square by rg, from where we can write that theta is equal to tan inverse of v square by rg. So this is also an important finding. What we understand from this, that if the body, it can be a vehicle, it can be a train, it can be a bus, if it is negotiating with a speed of v and the radius of the road, the circular path is r, then you must bank the road with an angle theta with respect to the horizontal, so as to facilitate the body to take a turn in that high velocity. Okay, so banking of the road plays a very pivotal, a very vital role in preventing the skidding, because it increases the force, the centripetal force, many folds. Okay. This is all about circular motion. We'll be now doing some problems in my next video pertaining to laws of motion, pertaining to friction, pertaining to circular motion. Thank you all. Thanks for watching. Thank you.